Good day, Jean-François from Chrysalide Electronics. We are looking at this buck converter with complete Kicad files, including schematics and PCB layout, bill of materials, and the files are available in the description below. It's free for download. We are going to review the design and how it was made in Kicad, and hope you find this little project interesting. You can take the file and get the board manufactured if you or include it in your own design. And let me know if you like this project and further projects coming. I designed this buck power supply and tested the design with buck and regulator output. And I open sourced this version of the design, which only includes the buck, with a modified version that includes a potentiometer to make the output voltage adjustable. And by calculation, we have a 3.3 to 13 volt output, and the input should be approx 5 to 16 volts. And 16 is a max absolute because this chip handles only 17 max absolute and we need some margin. And we are keeping the Aerosemi MT2492, which is a buck with a 2 amps output capacity. And it uses a 0.6 volt reference, which we polarize with this resistor bridge. And we use a trim pot with a fixed 2.7K and 10K trim pot. 4.7 micro at the output. 22 micro input outputs. I got into some of the details of this chip early on. So this is a typical diagram. We have used a variant of it. We have roughly 95, 94, 96% of efficiency. And this is the complete board layout. We include a port that is both input and output. We have V1 as a power supply. VSB is actually the output. SB for supply bus, supply to the user loads, and a ground pin, symmetrical pins on the header. And this is only for plated holes, inputs and output. J1 is the input side and J2 is the output side. And let's get into how we can design such a circuit in Kicad. So we put labels. V1 is our power supply from the external pin connections, and we label it so that we can place the label on the pin head over here. With J1 we'll receive VI and export V out on J2, and VSB is our connection to J2 and V1 is our connection to G1. We have V1, VF is the protection voltage, we just have the fuse in between. And if we check the component, we are using this particular fuse. We see the datasheet over here, Jean-François Electronics, and this is a 1812 surface mount. We are using the 150/16, which is 1.5 amps, 16 volt, and this will be our characteristics. We confirm 16 volts, 100 amp of max peak, 1.5 volt current, 3 amps trip current. Trip time at 8 amps is 500 milliseconds and 40 milliohm nominal minimum, 160 milliohm maximum. So we are confirmed to trip at 3 amps and we will hold for 1.5 amp at 25 degrees C, which means this will not protect our chip properly, but if it fails, it will protect from further damage. Footprint package, we select the chip, press F, and we will use the SOT 23-6 for the MT2492. We'll use the proper 1812 fuse L1812 with a hand solder variant footprint for the fuse. These are radial 6.3 diameter, pin spacing 2.5 millimeter. We see the LCSC reference is selected for some of these components. This is C1896. This one is not yet defined. This one either. And the chip is defined as 89358. And that's almost all for this design. There we have our power LED, which is C4410 for the resistor. 1206 1K our diode with this LCSC reference. When we have finalized this schematic, we get into the implementation on the layout. And to make this, we will use a VSB area on top and ground on bottom. So I laid up the back over here and the components according to the datasheet recommendation. We have spacing so that we can hand solder the components easily. And we see, provided we have the correct field area, there are some optimization possible. This VSB is taken from the ground, from the plane, the top plane, and where we need ground, we take it from the bottom plane like this. And we need also mounting holes and fiducials for manufacturing, and the big 22 micro capacitor. We use 0.5 millimeter for the high current and 0.35 for the signal or smaller current. This is all for the design of this board. We can even add some informations, like the dimensions of this board be 38 by 40. We used a 2-layer design. We don't need more for this simple board. The edge cut is for the PCB layout cut for manufacturing. Seal screen is the print on top and bottom. And finally the rendering, which looks like this in 3D view, top and bottom. To have this board CE certified, we will need to pass a EMC test, because the bug might cause some EMC emissions, or it might be EMC sensitive as well. And this design is now final and ready for manufacturing for the prototypes. We can check the BOM over here, and the bill of material, which is the part list, shows here all the components information, is including the LCSC reference. If we need, for example, manufacturing by GLC PCB, then we will need to complete a couple of components in there. We see the footprints, data sheets where they have been filled in. If we select a component and press G, the datasheet pops up. And to get a manufacturing file, we need to go in the PCB view, and from here we can export to GLC PCB or other manufacturer with export tool over here, like fabrication output files, jobbers, drilling, position, and if we install some of the plugins the manufacturers have made, like GLC PCB has made one of these, then we just click on it and we have a zip file with all the properly formatted files. And if we don't want to do it manually, we have to check, for example, when we import the Gerbers file, we will need to make sure that we have selected the proper options as mentioned by the manufacturer, if they have some specific options to be selected. This package is available at LCE website, link under the description, under Kicad source download link, which includes the Kicad source file. The project, schematics, PCB layout is freely available and includes just this adjustable buck stage, which receives unstabilized DC source and outputs plus minus 100 millivolt stabilized output. It's not a fully regulated output with a linear regulator. For some design we will need the second stage stabilization, for example to output regulated 5 volt or 3.2 volt if we do some analog measurement, or just supply the chip that provide an analog voltage stabilized reference for the microcontroller pins if we want to do accurate measurements, because this voltage source is not perfectly stabilized at this output stage. And we can check all of this using the test points over here. We will see on TP3 the output voltage waveform, and we can measure the oscillations in our scope to see the noise at the output and see if it matches for our circuits or we need further stabilization behind. Thanks for your interest in this project and channel. Hope to see you in the future for further coming projects.